I am very thrilled to introduce Tyler to you, who is a technology fellow for computational engineering at TWI and was the recipient of the NIST AM Benchmark 2018 award for rested stress predictions. On a personal front, he has 2 dogs, which he has very kindly written for me that they cause more trouble than behave. So I'm sure if you are a dog lover, you'd probably want to have a chat with Tyler at a later stage. Great. Over to you, Tyler.
Thank you very much. And yes, certainly, if you hear any kerfuffle in the background, no doubt it will be them as they start getting a bit antsy this time of day. Thank you for inviting us to talk this afternoon or this morning, whereabouts you may be. My presentation is very much, I think, actually, you've structured this very well because it's tying in a lot of the themes that we've looked at today, from some of the fundamental research that's going on to how industry is really trying to make benefit from the tools and capabilities of simulation to improve and enhance the quality and performance of additively manufactured parts. So this talk is all about how we can use process simulations, more or less straight to the point. Why even do modeling? You know, my colleagues in the labs with the machines, they would love to build a lot more parts and not do any modeling. But we'll kind of talk on where we see the biggest added value for that. And then also look at how this is really being applied from not just the powder bed fusion side of things, but also the direct energy deposition. So why do modeling for additive manufacturing? I think first and foremost, it's all about minimizing trial and error experimentation with virtual tests. May not necessarily be there where we can have a digital twin that's got this real-time double direction exchange of data, but trying to look at how we can get and use a validated model to replace physical tests, and then do some sort of optimization in that space, and then go back to the labs and build something in a much more targeted manner. A lot of modeling is about understanding why we see what we see. When we're doing these large process parameter optimization activities, we might see things that aren't particularly clear what the direct link is between the processing conditions and the quality of the part. And models let us measure and estimate things that we can't very readily do in the real world. Uncertainty is a fantastic area, and Stephanie was speaking about this earlier with lattices. Your lovely CAD model of your lattice will behave very different than the actual one that you print that's wobbly, warped, and full of all sorts of imperfections. So really understanding how that uncertainty in the powder feedstock, the chemistry, the maintenance of any preheat or post-weld heat treatment control can really be investigated with a model to understand how that puts a scatter band on the expected performance. Of course, through life performance, we almost want like a passport that travels with it, that captured all of the imperfections or manufacturing defects that occurred, what it was subjected to from a post-manufacture treatment, whether that was surface, heat treatment, hipping, and then all the sorts of cycles that it sees during its life. And ultimately, if we tie these together in a nice way, we save time, we save money, and we accelerate that long period of time between conceptual design and actual fabrication and use in the field. So I like the snapshot on the left. It's a bit of an abuse of the results, but I like to go through it. But really, empirical studies alone don't give us the real insight into process features and property relationships. And even if they did, they're incredibly costly and time consuming. If we look on the left, you've got some SN curves for the fatigue performance of a TI-64 part. And you want something to last, say, 1 million cycles, you can find any stress range on that plot where it failed. Now, yes, that's a little bit of an abuse because some of that's machined and hipped and not hipped, but it's very indicative and representative of what we see with a lot of fatigue behavior of additively manufactured parts. It's not just down to a material, but it's the material, the process parameters, the surface treatment, and any number of factors that ultimately influence the performance of that part. And if we look on the right, we built 2 walls. Both of them were about 1 inch wide, about 10 inch tall, about 15 inches long, and same material, 316 stainless steel. So same feedstock, same geometry, approximately the same energy input. Look visually, nice shiny pieces of metal, But if you cut them open, you can see on the same length scale of these micrographs, maybe 2 or 3 different melt pools. Whereas down here from the powder bed fusion side, whereas this was wire arc, you've got thousands. You've got a dendritic structure in one and a cellular structure in the other. So although visually they're the same, materially they're the same, of course they're going to have incredibly different properties in texture and strength and fracture toughness. And we can build these walls and test them and cut them up, but we can also start to get insights into why that's happening and how we can control their performance if we have modeling and simulation that runs in parallel. But realistically, we can't predict everything with good certainty, but we can get that insights. And what we try and work at TWI is that pragmatic application of these advanced technologies in a way that industry can get benefit from them. So what's a manufacturing process simulation? I think Professor Toe said this very well. If we look back at inherent strains and eigenstrains, they were developed in the 70s and 80s to accelerate distortion predictions for shipbuilding activities. Because doing a thermal mechanical model with 100 different weld passes and then trying to put that inside an optimization loop just isn't feasible. But what we try and do is translate a process into a mathematical model, validate it, make sure we're confident in it, and then use it to calculate the key performance indicators. Could be distortion, like we were looking at earlier, could be residual stress, could be the buildup of heat in the thermal transients. And then we use those results to go back and improve the process itself. And there's no one-size-fits-all model. It could be a model for detailed residual stresses in a nuclear application like we see on the right. There we're looking at bead by bead and really, detailed constitutive behaviors. But if we're looking at weld sequence control for distortion, it might be a much higher level model that's capturing only the physics that are relevant. And the same is true for additive manufacturing. We're using a existing thermal mechanical modeling framework, but trying to put in the right ingredients to calculate what we need. So I'll take us through some work on powder bed fusion. Very small scale, so a lot of challenges and runtimes that were discussed earlier. And we feel it's so important. There's a lot of click button software available, and CAE technologies are getting democratized and easier to use. But you've got to have that confidence that these lovely, in my opinion, kind of nice animations agree with the real world. So for powder bed fusion, we've designed some substrates that we can thread thermocouples about 200 microns or less below the build surface. And then we can feed the wires out through some excess powder overflow pipes in the machine, in this case, a Renishaw AM250. And we can collect thermal data that we can then use to compare against our model. And we can use thermal imaging as well to look at the sort of ejection of particles and energy loss and the size of melt pools. And through calibration activities, representing scan strategies with high fidelity, we can gain confidence in that thermal model. Confidence in the thermal model, we can start to look at things like how the microstructure changes. Again, adapting mature capabilities from the welding engineering world, where we look at solid state phase transformations in ferrous alloys and others. We can do the same for titanium alloys, where very rapid cooling takes us from a BCC high temperature beta stage into something more acidic, where slow or more diffusive transformations can take place if we don't cool so rapidly. And ultimately, the temperature and the temperature transients determine the microstructure, and the microstructure determines the mechanical properties. So if we want to know how this is going to perform, we need to start linking all these variables together. And again, it's great to translate things like continuous cooling diagrams or time temperature transformation kinetics into our finite element models or simulation methods, but we've got to validate that, because a lot of those diagrams and kinetics were made for cooling rates not nearly as severe as we see in additive manufacturing. For those familiar with titanium alloys, this isn't a very pretty picture of a titanium alloy. It's incredibly fine-scale martensitic structure. And so if we talk about this part being TI64, and it goes back to some of the questions about the lattices earlier, we need to know, what does laser powder bed fusion printed Ti64, how does that behave compared to off-the-shelf properties that one might get from literature for wrought or cast product? And of course, as we go into higher scale physics and to smaller scales, we have to accept that the uncertainty quantification is going to go up. And so there's going to be less agreement, and we need to be pragmatic about how we use the results in a deterministic or predictive manner. But it's not just phases, alpha and beta and martensite that influence properties, but also the solidification microstructure. And that's really important. So as this cools from liquid, we will get nucleation in the melt pool and on the boundary of the melt pool. And then those grains will grow, and they'll grow dependent on the melt pool size and the thermal gradient. And as Professor Toll was highlighting earlier, often we just do process parameter optimization on a nice tiny square section column or cube. And then we apply those parameter sets to something that's incredibly topology optimized and complex. And we shouldn't be surprised when that doesn't work out necessarily very well, because as heat builds up, it changes how the material is responding and solidifying in the transformation kinetics that take place. Link all of these hierarchies together, dial into regions, do some fancy calculations, dial out, get macro scale residual stresses, and then we can put it to the test. So in this case, we built some cruciforms out of Ti64. One was in the as-built condition on the green, and then one we gave a conventional heat treatment at about 800 degrees for 2 hours. We then cut out vertical and horizontal tensile tests to see how well we can estimate and predict how these parts are going to behave. Now, Ti64 is a two-phase material. It's got an alpha phase and a beta phase. One gives us good strength, one gives us good ductility. And getting the right balance is really important. But getting the right balance usually requires nothing cooling nearly as fast as AM. So when we look at this X-ray diffraction pattern, we see almost no beta phase present in the black curve, which is the as-built condition. It's cooled so rapidly, it's all been consumed into a martensitic phase. And so we should expect there's almost going to be no ductility. And when we do the tests, we see that exactly. Now, if you were to look at, say, an aerospace manual for Ti64 properties, it'd give you a yield around 1100 megapascals and a UTS around 1170. There's very little strain hardening. But the red and the black curves are in the as-built condition. They've got a much higher, much more elevated yield strength because of that martensitic, very hard phase. But their ductility is significantly less. And we also start to see some variation in ductility depending if it's vertically orientated, pulling layers apart, or horizontally orientated, pulling layers transverse to the prior beta grains. And so this is why it's important to have not only just the phase transformation kinetics, but also things like the solidification texture. And we can see once we take this AM material, we give it a nice heat treatment, the purple and the green curves give us what we'd expect of Ti64 to behave. So we can do this, we can do these process simulations of the cruciform, dialing in just to the gauge volume of the dog bone specimen, removing that dog bone specimen with all of the nice tracking of the phases and the solidification structure. And then looking at those phases and the orientations and assigning them local properties. And then we can do the simulation of the tensile test and recover within reasonable accuracy the behavior that we'd expect of the as-built and the heat treated. And this can help us start to understand that link between the process conditions and what kind of heat treatment we might need, which might be very different from a conventional heat treatment for Ti64. And this is activity that industry is starting to use. They're really wanting to minimize the amount of trial and error experimentation and understand how they can get consistent and homogeneous properties throughout their build, which might mean tailoring the process parameters to geometric features or as the height gets bigger in the build chamber. And just to give a similar example on nickel-based superalloys for direct energy deposition, powder bed fusion is lovely. It creates nice intricate parts, but you're limited by your build chamber size. Whereas with direct energy deposition, it's open architecture. We can just deposit material, move along a path. We might not be able to have the geometric freedom that we have with powder bed fusion, but we can build much bigger scale engineering parts. And again, we like validation. So as opposed to sticking a thermocouple substrate, here we have a reusable, recyclable thermocouple substrate where we can place contact thermocouples underneath a part or underneath the build plate, build directly on top of that. And this is so important for that confidence in your thermal model before you start running ahead to distortion and residual stress and microstructure. And the nice thing is you can just unclamp it, put something else back on it, and deposit in different styles and replicate that in your model. And then with nickel-based superalloys and with direct energy deposition, there's a continuous challenge around lovely equiaxed microstructures and columnar microstructures. And we often get columnar. The grains just start selectively going taller and taller and taller, down selecting to fewer and fewer ones. And this can have a really detrimental impact on the toughness and the strength and isotropy, as well as the fatigue behavior. And there's what are called GR diagrams, where we can look at how the thermal gradient and the solidification rate can trigger one formation or the other. And we can use that information and put it in a model and start to understand this dialing and changing of heat input with different geometric features to achieve a more consistent and uniform structure. And the proof is in the pudding. We can see here a bunch of different walls. These are cross-sectional slices of the walls that were built with Inconel 718. Same material, same geometry, same power, about 2 kilowatts, different travel speeds. And just that change in travel speed was enough to trigger very, very different solidification microstructures. Some exhibit this railroad track down selection of preferential grain orientations. Others have a much more mixed structure. Quite a few of these are totally undesirable from a mechanical point of view, but if we can understand why we get certain ones, then we can start to change the parameters virtually without having to constantly build and change parameters in the wall. And so just to summarize these last ones, we can see how these models can look at melt pools and their overlaps and how they link together and how all the changes of the speed relate to that. And we can link them to precipitation kinetics and link that to the strengthening mechanisms. And again, like we were doing in powder bed fusion, we can have tools to understand how our materials behave and how we can improve them. So just to summarize, modeling, I think, is crucial to the acceleration of AM technologies and the wider adoption. We can link process parameters to defects. We can link process parameters to the buildup of heat and distortion and to the microstructure. And if we use the right models in the right ways, we can start to really minimize that experimentation aspect, target it where it needs to be targeted, and accelerate the adoption. So thank you again, Ajit, for inviting us along, and I'm very happy to take any questions.
Brilliant. Thanks, Tyler. Yeah, we easily have a few minutes for questions. Perhaps I could start with the icebreaker question here. So Tyler, we've seen quite a few presentations earlier as well, and I think your simulation along with the experimental validation work, it seems like currently the community is working at different length scales. So what challenge do you see in terms of offering what Andrew posed as give us simplified design tools? What do you think we might need in order to bridge this gap of different length scales where some people are looking at part scale simulations and in other case we're looking at more process level?
Yeah, it's a good question, and it's a really tricky one. I think probably what Andrew highlighted on interoperability is the biggest barrier. Being able to take what my Renishaw or my EOS machine and its pre-compiled build card is doing put that into a model and simplify it, or being able to take different microstructure kinetic models and integrate those into different ones. The data exchange between different processes is a big barrier at the moment. And even the sort of CAD to STL to process simulation to slicing, all of these issues are quite big barriers. And I think the link scales and the time scales it's going to be there for a while, probably, because it's such a challenge to dial into regions of interest and keep that fidelity for your whole structure.
And similar to, I guess, what Albert had shown in his work, do you see perhaps moving from CPU to GPU may start having some form of acceleration in the modeling that you're performing?
Yeah, totally. I think any advances in just the speed of computation will be very welcome by industry. Absolutely.
Are there any other questions for Tyler? Of course, feel free to post them in the chat and Tyler will get back to you. Yeah. Okay, I don't see any. So thanks, Tyler, for giving us a lovely